Okay, welcome. We've got a long weekend. Don't come to class on Monday. You can if you want. Nobody else will be here. So, no class on Monday. Wednesday, when you do come back, homework 2 is going to be due. And I noticed that some people have already submitted that assignment early. That's great. I'm glad that people are getting an early start. Just as a reminder about scanning homework assignments, I recommend that you use either a plain unlined printer paper that's just blank completely or engineering computation paper. But graph paper or lined notebook paper doesn't turn out good in terms of being easy to read for the grader. And especially when we start doing cash flow diagrams, they don't really lend themselves to notebook paper. So please pay special attention to the quality of your scans and make sure that the pages are in order, that they're all oriented correctly and not sideways, in focus, well lit, contrast, grayscale, or black and white. So homework 2 due on Wednesday. Today we're going to continue talking about the way that cash flow diagrams should look for the standard uniform series and also for gradients. And of course I've got an in-class exercise for us to do some practice problems. So does anybody have questions before we move on to today's material? All right, so let's review. We've talked about annual series before. And some of the characteristics of an annual series is that the amount is the same every year and that it's consecutive time periods. So if there's a situation where you've got a cash flow diagram that has several years that are the same, and then there's a gap, and then several more years that are the same, this would be 2 different annual series, not a single continuous annual series if there's a gap. And so you'd have to treat them separately. And then, you could find the equivalent value of the first annual series with n equals 3. And then you could find the equivalent value of the next annual series, in this case with n equals 4. And then once you had here at time 0, one of them already at the present, and then this so-called quasi-present value at time 4, you'd have to move that back to the present as a single lump sum. So it would be find P given A for the first step, and then for the next step, this would look like an F. And so then you would be find P given F. So an annual series is continuous. And remember our standard notation in terms of like what we put inside of the brackets. In this case, where the annual series is given and the present value is unknown, then it's find P given A. So P slash A, we define some interest rate for the problem and the number of periods. And remember that the periods aren't necessarily always going to be years. You might have a homework problem, for example, where I tell you the annual interest, and then I say that it's monthly compounding. And so if it's a problem like that, you'd take the annual interest rate and divide it by the number of compounding periods per year, and then that would give you the interest rate per period. And then n would be the number of total periods in the cash flow. We can also have problems where we're finding A given P. So this kind of problem, the first one maybe would be if you have an idea of what your future revenues are going to be, then how much could you justify spending at the present to purchase some piece of equipment? This is just like if we think in real terms, what kind of a real world problem would this be? Maybe if you're starting a lawn care business and you want to know how much you could afford to pay for all of the equipment that you're going to need. So you'd have some idea of what your future revenues are going to be, and then you'd find out what's the lump sum equivalent of all of that. So this other kind of cash flow where the annual amount is unknown, maybe we can think of that in real terms of if you have already just purchased the equipment, how much should you make each period to justify the lump sum investment that you've made. So in this one, it's find A given P. If we think about what's in the parentheses there, the interest rate per period, the number of periods, and then the present value is always one period before the first of the annual series. And I talked about this in class on Wednesday, that if we also had an arrow at time 0, then that would be combined with the present. It wouldn't be part of the annual series. So like if there was an arrow at time 0, don't be tempted to think n is 1, 2, 3, 4, 5, 6. N is just the number of periods after time 0 for an annual series. Okay, so any questions on that refresher? Now what about a future value? We can sometimes have an annual series and we want to find out the lump sum future equivalent of that. So the major difference I'll point out is that the lump sum future value occurs in the same year as the last time the annual series showed itself. So it's a little bit different from when we're having P, where P is 1 year before the annual series, but F is in the same year as the last value. So the real-world application of a problem like this might be if you were going to receive a bunch of payments over time and then you had to pay back to the bank as a single lump sum, then how much would that lump sum be? And it's a little bit strange that you're going to be paying back at the exact same instant that you're receiving some money, but that's just the convention for the find F given A. And the same thing is true if F is a given and A is an unknown. F and the last A occur in the same time period. All right, so you've got that in your notes. You're going to keep it in your mind. It'll come up again. But any questions about future values in uniform series? Okay, so let's just look at an example. If we have a uniform series where it says here an industrial engineer made a modification to a chip manufacturing process that will save her company $10,000 each year compared to previous expenses. So we consider that as a revenue because money that the company used to spend has been saved through some improvement. So that's booked as a revenue. So we have an inflow of $10,000 each year for 7 years and an interest rate of 8% per year. So let's just summarize how we would express this problem. That's a lengthy, lots of words, lots of characters here, but we can distill the essence of the problem really simply by just saying this is find F given A, I equals 8% and N equals 7. So that's way less symbols than all of this language. And all of this language may have some ambiguity. You'll notice here in parentheses I said, what is the equivalent lump sum value in year 7? Because somebody might read the first part of this and say, well, how much will the savings amount to in 7 years? Maybe they don't know the time value of money idea and they're thinking you just 7 times 10,000 equals 70,000. But we can't do that because if we draw a cash flow diagram of what's happening in this problem, we have 7 years of revenue, 10,000 each. So 1, 2, 3, 4, 5, 6, 7. All right, and I equals 8%. When there's an interest rate that applies, it's not meaningful to add together money in different years. Like the $10,000 in year 1 has a different value than the $10,000 in year 2. sometimes just for the simplicity of contracting, we'll say that the amount due or the amount we're earning each year is the same, but that doesn't mean that each of those dollars has the same value. So you don't add money together that's in different years unless I equals 0. Then you can add the money together because there's no compounding and no discounting. But if there's an interest rate that applies, you're never going to add money together that's in different time frames. So this is saying, what is the equivalent lump sum value in year 7? So if we're going to find out how much is F, then what we do is go to the table. This is the 8% interest table. We go to the find F given A column. And here in parentheses, find F given A, I equals 8%, N equals 7 is equal to, and now we look up the factor. It is 8.9228. So the way that we use that then is we just know that the ratio of F to A is 8.9228. And so then therefore F is going to be the annual amount of 10,000 multiplied by 8.9228. So it's kind of interesting. What it's saying is you don't just add $10,000 together 7 times. There's actually going to be more future value there because the money is compounding as it moves forward in time. It's kind of like it's earning interest. This amount from year 1, it earns 1, 2, 3, 4, 5, 6 years of interest by the time it moves to year 7. And then this lump sum that was at year 2, it earns 1, 2, 3, 4, 5 years of interest before it gets to year 7. So this ratio takes all of that compounding into effect. It's the same as if we had find F given P individually. If we did it like 1 year at a time, find F given P for year 1 with N equals 1, 2, 3, 4, 5, 6. Find F given P for year 2. Take it to year 7 and so on. So $89,228. 1, 2, 3, 4, 5 digits of precision. So 1, 2, 3, 4, 5. If we had done the equation method instead of the factor method, then we could have reported accurately to the nearest penny. But we use the table lookup values, then we have to be sensitive to how many digits we had in our factor. So F is in the same year as your last annual amount. All right. Gradients. Gradients is where it gets a little bit tricky. So imagine a contract where either you're getting money or you have to pay it. One or the other, doesn't matter. But the amount is going up every year. So maybe like in the first year you don't have to pay anything. In the second year you have to pay G. The third year 2 times G. So if G is like $100, then what this is saying is like at year 0 is the present. A year from now you don't owe anything. 2 years from now you have to pay $100, then $200, $300. So it's going up. The amount is going up every year. Then what would be the present value where the series, instead of being constant every year, is increasing by a regular amount? So that is an arithmetic gradient. So this first illustration is showing find P given G. And the important thing to point out is that in year 1 is 0G. So you don't see the effect of the increase until year 2. In year 2 is when it starts getting gradually larger. Oh, by the way, I got a good question during my office hours earlier this week. See this little ... in the cash flow diagram? So it's year 1, year 2, year 3, year 4. If you have a really long cash flow diagram, let's say if you had 60 years, I mean, you can brute force it and write all 60 years out, but if it's the same, instead of doing that, maybe what you could do is say, okay, here's year 1, 2, 3, 4, 5, and then we'll just put like a gap. Rather than repeating ourselves 60 times and going crazy from the tedium of it, you know, here's 59 and here's 60. So see how I've broken the line there and we've got the little dot, dot, dot? This would also be an acceptable way of representing a cash flow diagram where you have an annual series, some amount. So you're kind of truncating the length of the cash flow diagram and showing that it just continues uninterrupted in the same pattern that it was before. So that may save you a little bit of graphite on your paper for the homework assignment. All right, so back to gradients. This is find P given G. It's the same kind of G starting in year 2 if we are finding G given P. So the key thing that never ceases to cause mischief is that in an annual series, the A begins in year 1, but in a gradient, the G begins in year 2. So we'll get some practice with that just to drill it into your mind and get you accustomed to the convention with that. All right, let me pull up the in-class exercise and I'll hand it out. The first problem is just to warm you up a little bit, and then problems 2 and 3 are dealing with gradients.
Oh, I got a half-inch binder, but I have the other.
Let me just interrupt you for a quick second and mention something. Gradients are the same as annual series in the sense that F is in the same year as the last amount. So you know how an annual series, if you convert it to an F, the F is in the same year as the last A? The same thing is true here. I showed you the diagram of what it looks like for P versus G, but G versus F, it's that case where F is in the same year as the last bit of the gradient. So you'll need that for problem 2. So the solution to the first one, let's look at that. So this first one's just a warm-up. Review. You give a $7,500 loan at 8% interest, and the loan should be repaid in equal amounts over 8 years. How much should each annual repayment be? So P is given. The problem doesn't say when you gave the $7,000 loan, but since there's no other transaction specified, that's the first one. We'll consider that to be the present, the now, times 0, when everything else is based from. So P is 7,500, I 8%, and N is 8. And it's annual repayments. Okay, so I just summarized the problem in terms of, what's in the parentheses there. Find A given P, I equals 8%, N equals 8. So the factor from that is 0.17401. It doesn't say that you had to use the factor table, so if you choose, you could have calculated your own factor using the formula. So which formula would you use? Find A given P. This is the formula that you'd utilize for that, calculating your own factor. So it should be $1,305.10 is how much each annual repayment installment that you receive, it should be. That's the economically equivalent value. 8 payments of $1,305 is the same as a lump sum of $7,500 now when I equals 8%. So any questions about that first one? Okay, so the second one, I ask you to start off just by writing the years on the cash flow diagram. Like initially it was blank. Now why did I do that? It's just to force you to look at the fact that the first time you see the gradient isn't until year 2. It's to kind of, give you that kinesthetic impression that the gradient first kicks in year 2. So 0, 1, 2, 3, 4. Okay, so the value for n in this gradient is 4. N equals 4, and the value of g, it's increasing by a constant amount of 200. So g is 200. And find the present value. So use the P/G column. Okay, so this problem is find P given G, I equals 8%, N equals 4. So if you go to the table, the 8% table, find P given G, N equals 4. And just to verify, this is the 8% table. Yes. So the factor is 4.6501. And so if you multiply that by G, then the lump sum equivalent of that is $930.02. So why is it so low? If you just added everything together, that's $1,200. So you can either have $1,200 over time or only $930 at the present. Those two are economically equivalent. And the reason why it's so low, it's not the same number of dollars, it's the same value of dollars, not the same number of dollars. And so the value in time 0 is greater than future amounts because those future amounts are being spent on goods that cost more due to inflation. So the $600 in year 4, if you discounted that to the present at 8% each year, it's like saying 600 takes an 8% discount to get to year 3, then another 8% discount, then another 8% discount. So every year you move that value backwards in time, it's taking an 8% discount. And that's why the single lump sum present value is so low. And then the third part, I ask you to use the equation method. So the F/G equation for part D. Find the lump sum single value in year 4. So the F/G equation, here's that. 1 plus I to the n minus 1 divided by I squared. And then that whole quantity, subtract n divided by I. So we've got a bit of a jumble with the formula there. If you do it in multiple steps, that's the good habit. The bad habit's just putting it into your calculator and hoping that you didn't type it in wrong. The good habit is actually writing the formula on the page, and then the substitutions, and then show your intermediate calculations along the way, and then the final answer, and then double check everything to make sure that your finger didn't slip or that you didn't see things the wrong way the first time around. When you're designing important things like medical devices or, power lines or bridges or buildings, you got to be pretty accurate. There's very little margin for error, or money, you know. Nobody wants error with their money. So 100% accuracy is what we're aiming for. So write out all of your calculations as lengthy as you can. Every step illustrated. So we find the factor and then multiply it by the value of g. So expressed as a lump sum in year 4, the equivalent value is $12.65 and 28 cents. And we're accurate to the nearest penny here because I calculated the factor with as many digits as we need. All right, so I'm going to pause again to allow you to finish up the third problem now. The whole is just the sum of the parts. So you can split apart a cash flow diagram if you notice that it's combined with an annual series and a gradient. You can basically separate those two parts, and that's what this is showing here with my sketch. I'm saying there's an annual series in the amount of 400 with n equals 5, 12% interest rate, and then there's a gradient where the amount is 30. And so what I want to do is find out what is the individual value of the gradient part of it, and then what's the value of the annual series part of it. And then if you find the value of the two components, we can add it together. So we can find the present value of the annual series. So here's that, where I'm just find P given A with the equation method. So showing the formula, showing the substitutions, the intermediate calculations, and then the final factor that is determined. So $14.41 and 91 cents is the present value of the annual series. And so that was the regular $400 outflow every year for 5 years. And then the formula for the present worth of the gradient, we substitute in I equals 0.12, n equals 5, and the P divided by G factor should be 6.3970. So then the value of the gradient at the present is $191.91. So the total is just adding up those two together, and it's $16.33 and 82 cents. Since we still have 5 minutes, I want to give you a glimpse of the future and the increased complexity that we're going to be facing very soon. So both of these, it was kind of easy because time was already at time 0. But in Wednesday's class, I introduced the idea of like a quasi-present, where a certain time period isn't actually the present, but we briefly pretend like it is. So look at the cash flow diagram I've drawn on the whiteboard here. The cash flow diagram is showing an annual series and a gradient. But this is different from the problems that you've just done in the in-class exercise because it starts many years offset into the future where there's just nothing happening for several years, but then it begins. Okay, so think in terms of strategy. Like if you were a chess master and you're having to think into the future or like map out what your steps are, we want to find out what is the present value equivalent at time 0 of all of those amounts. So there's two approaches. You could either brute force it, where you're just each individual year find P given F. So you could do that over and over and over for every year, but that would be tedious and inelegant. It would be a little bit more sophisticated if you said, okay, here's an annual series and a gradient. So here's my annual series. My annual series has 1, 2, 3, 4, 5, 6, 7, 8 years. And so if here's my annual series, if I find P given A, okay, so in step A, what we're doing is find P given A. Okay, so there's this arrow, the amount that's in year 3 we got from find P given A. Then how do we get that to times 0? What would be our next factor that we'd apply?
Find P given F.
Good, that's right. So we'd take it from A over to year 0. So take A to year 0 with find P given F. So initially we pretend like this is the present. We know in the back of our mind that year 3 isn't really the present, but it's just like what we have to do to consolidate an annual series into a single lump sum, is we pretend like year 3 is the present. So we find P given A, and then we say, well, actually, that's a future value. So find P given F. That would be our next step. Okay, then we've got a gradient. So we took care of the annual series. Where's the gradient? G is 100. But when does the gradient actually start? Like where, if you find P given G, where would that lump sum be? It would be at year 6 because it's 0G, 1G, 2G, 3G. So this is our new quasi-present. So we would find a lump sum. So like B is the equivalent lump sum of the gradient. Find P given G. And then how would we finally get that to year 0? Take B to year 0 with find P given F. Now, in this first find P given F, it was n equals 3. What's the n for that one? Well, it's in year 6, so n equals 6. So next week, we're going to have like tricky problems where you have to think in multiple steps to move the money through time. Okay, it's 12:50. We're out of time. Just as a reminder, no class on Monday, so I'll see you Wednesday.